All right, so we've talked about equilibrium and how chemical equations can come to equilibrium when the forward and the reverse rates are equal to each other. What we want to look at in this video is something called the reaction quotient. Now, luckily for us, this reaction quotient is very, very closely related to the equilibrium constant. So if I have, say, this reaction, so 2NO2, I'm going to go to N2O4, and these are both gases, right? I can write an equilibrium constant for it in terms of the products and reactants, and we went over how to do that already. But what I can also do more generally is I can write a reaction quotient, so reaction quotient, and we'll symbolize that with a Q, and I can calculate this reaction quotient in the same way. So it has the same form as the equilibrium constant expression, and I can say that it's the concentration of N2O4, so my product, divided by my reactant. So if it has the same form as the equilibrium constant expression, what's the difference? And the difference with the reaction quotient is with Q, the concentrations don't necessarily have to be at equilibrium. To necessarily be at equilibrium. Okay, so what I can do is I can take any given set of concentrations, or if you're comparing it to a Kp partial pressures, I can take any set, I can calculate a reaction quotient for that specific state of the chemical reaction. Now, why would that be useful? The reason why this is useful is comparing the reaction quotient value to the value of the equilibrium constant for the reaction at that temperature allows you to see two things. First, is the reaction in equilibrium? And second, if it's not in equilibrium, how's it going to establish equilibrium? Is it going to form more products, or is it going to form more reactants? And so when we look at this relationship between Q and K, if Q and K, this equilibrium constant, are equal to each other, then the reaction is at equilibrium. And more generally, what we can say is that the concentrations that were given describe what's called an equilibrium state. Okay, so if you calculate a Q and say, hey, that's equal to KQ, then there's not going to be a change that's going to happen. It's already at equilibrium, and it's going to stay with that set of concentrations unless you do something weird, like add more stuff or change temperature or whatever. But maybe more interestingly, if Q is greater than KEQ, then this means that we have too much product. Okay, that top part, the numerator, is too big compared to KEQ. So we have too much product, and sorry about that, and the reaction will form more reactant to establish equilibrium. And it's going to do that by using up product. So if Q is greater than KQ, some of the product, I'm just going to use my general equation here. Okay. So some of the product would be used up, and it's going to shift that way. Okay. And then the other situation, if Q is less than KEQ, then we don't have enough product. Okay. And so if Q is less than KEQ, we have too much reactant. And we would say that the reaction will shift to the right. Okay, so shift right means more product's going to be formed because there's not enough product to establish equilibrium. And so some of these reactants will be used up and we're going to form product. So this is the case. This is what happens if Q is greater than KEQ. What happens if Q is less than KEQ? Okay, so by calculating these reaction quotients, we can see if this is an equilibrium. And if it's not, Are we going to form our product? Are we going to form a reactant? And there's all kinds of wonderful questions that you guys can be asked about, changes and how much and which way is it going to shift. And we will get to that in class. Okay, so I just wanted to have you guys get this in your notes. And then next class, we will look at how we can use this to analyze chemical systems.